Hi, my name is Stella Sue, and my project is on domain-agnostic self-supervised contrastive learning for computational histopathology. While deep learning has demonstrated remarkable performance on medical imaging tasks over the past few years, a performance drop is observed when deploying a model on data that is out of distribution from its training data. This can be caused by variations in slide scanners, protocols for staining, and medical sites. This phenomenon is known as domain shift and will often hamper the clinical applicability of ML models. Self-supervised contrastive learning is a promising subclass of unsupervised learning and is used to learn representations from unlabeled data. These representations can then be used for downstream tasks. Self-supervised contrastive learning is generally developed for natural images. However, image augmentation, which is a critical component in self-supervised contrastive learning, has not been intensely studied when applied to histopathology images. Moreover, histopathology-specific augmentations have not been applied to self-supervised contrastive learning. The goal of my project is to develop a novel algorithm that incorporates histopathology-specific augmentations into self-supervised contrastive learning in order to learn representations of histopathology images that will be robust to variations across domains. Next, I applied the representation learned from my self-supervised contrastive learning model to downstream applications like tumor classification and mitotic figure detection. Through this, I will be demonstrating better domain generalization and compensating for scarcity of labeled datasets. Let me first introduce the concept of self-supervised contrastive learning. In self-supervised contrastive learning, two views are generated for every image using augmentations. The encoders will then generate visual representations from these image views. These representations are then projected through an MLP in order to lower dimensional features, and images undergoing different augmentations but coming from the same histopathology images are used to create similar samples, while augmented images created from a different histopathology image are dissimilar samples. The SSL model is then trained to learn a representation that maps similar samples closer and dissimilar samples farther apart in the embedding space. In this project, I chose to use the MOBI algorithm, which is a combination of two popular self-supervised contrastive learning approaches, MoCo V2 and BEAL. I chose this algorithm because of its great performance even when using a relatively small batch size of 256. For generating the two different views from unlabeled data, I used 3 histopathology-specific augmentations in addition to augmentations typically applied to natural images. The 3 histopathology-specific augmentations used to generate the 2 image views were stain norm, stain aug, and style transfer. In stain normalization, you normalize histopathology images based on a chosen reference image. In stain augmentations, you first perform stain separation to separate the hematoxylin and eosin channels, and then you apply random shifts to these 2 channels before converting them back to RGB. Instead, style transfer, you use adaptive instance normalization style transfer to generate stylized histopathology images from artistic paintings. For training my SSL model, I created an unlabeled dataset consisting of 19 different public histopathology image datasets. The dataset had approximately 21,000 whole slide images, and in order to diversify my dataset, as the success of the contrastive pre-training method heavily relies on the diversity of the dataset, I also included histopathology images of 14 different organs. Next, I generated 1.1 million 224 by 224 tiles by randomly sampling tiles from each of the 21,000 whole slide images. However, due to GPU resource limitations for training my SSL model, I had to create 2 subsets from the original, tiny and tinier, the former having 10% of the full dataset and the latter having 1% of the full dataset. To evaluate the encoder trained from the SSL model, I froze the encoder in a typical classifier architecture, only training the linear layer on top of the feature representation generated from the encoder. This was done using the Wilds Chameleon 17 dataset, which is a dataset that has the domain shift issue, making it much harder to solve compared to simpler classification tasks in histopathology. As you can see, the dataset with the domain shift the model with histopathology-specific augmentations performed significantly better with an RARC of 0.985 compared to the baseline method, which has an RARC of 0.806. I next took the best performing SSL model, which was ResNet50 with style transfer, and trained the model using fractions of the training data in order to evaluate label efficiency. My model, using only 10% of the training labels, was able to outperform its fully supervised counterpart, which uses all of the training labels. This demonstrates that SSL can compensate for scarcity of labeled datasets. Another main goal of unsupervised learning is to learn features that are transferable. So in order to further evaluate my SSL model's performance, I compare it with ImageNet supervised pre-training when transferred to the downstream task of mitosis detection. The problem also deals with domain shift, making it much harder to solve compared to typical object detection tasks in histopathology. For this task, I use Bretonena, which is a state-of-art object detection method, where I also use the best-performing SSL model, ResNet50 with style transfer, as the backbone. My experiments show that when transferring features to downstream mitotic figure detection tasks, unsupervised pre-training surpassed its ImageNet supervised counterpart by a large margin for both the 3 times and the 6 times schedule. My experiments indicate that my algorithm, SSL with histopathology-specific augmentations, can effectively improve model performance on histopathology data with domain shift and compensate for scarcity of labeled datasets.